Today, we learned about risk and hazard, types of types and scales of zonation, seismic zonation of India, and a bit about surface waves. So, before we go any further, let's have a
bit of a recap of what we learnt yesterday. So, in the previous class yesterday, I showed you some of the research work from my students. Thereafter, we had a discussion about what is risk and how it is different from hazard. So, in this particular thing, I told you that the hazard is naturally occurring phenomena that has capability of causing loss or damage in an area, while risk is the probability of something that is getting damaged from that particular hazard, and the seismic vulnerability is the inherent weakness of a system or structure or the area. So, risk is nothing but it is the convolution of vulnerability and the hazard. Thereafter, we took some examples how if the hazard is same but the risk can vary. So, we took the example of California, which has a network of long faults. Let's suppose if you consider a single fault which is quite long and passing through a populated area and also from a remote area where the population density is quite less. So, you can understand the hazard is same, but risk may vary based upon the density of the people living in there. Thereafter, we discussed about this pie chart, and we saw that among all the natural disasters happened in the 20th century, more than 50% casualties happened because of the earthquakes all over the globe. And if you look at the earthquakes and compare it, the casualties with respect to the important regions in the world, then the Asia and Pacific suffered more if you compare it with Africa, America and Europe. That quite naturally because of the bad and poor construction designs of the buildings over there. Thereafter, we discussed about this particular collision plate boundary in the northern part of India, where the Indian plate is colliding with the Eurasian plate, and because of that friction, a lot of more than 8 magnitude have been witnessed by this particular region. And also in this slide we discussed about the seismic gaps that are there along this plate margin boundary, and there are 3 seismic gaps we discussed about. This is the Assam gap, and here you have the central seismic gap, and this is the Kashmir gap. And then we have discussed about the seismicity in the Indian subcontinent, and we marked major epicenters for different magnitude range, and you can see the cluster of the earthquakes are mostly located in the plate boundary region, and there are chunk of earthquakes in the southern India or the peninsular India. Although the peninsular India, because they do not follow the construction designs, so the earthquakes are equally damaging even though their magnitudes are small. And on the right you have one of the complex geologically and tectonically the region of northeastern India, where you have we have marked 3 important earthquakes: 1950, this Assam earthquake, you have this 1897 Shillong earthquake, 1934 Bihar Nepal earthquake. And I told you that this region is complex and a lot of earthquakes are happening because of the collision plate boundary, and also the subduction is happening to the west. Now thereafter we started with the seismic zonation, and in seismic zonation we divided the geographical areas based on their potential to the earthquakes, and the zonation can be done on national, regional, local or site specific levels. And if you consider a bigger area for the zonation, then number of zones, if you are making it lesser, then it will be a very simplified representation of the hazard. So for construction of the seismic zones, you need to take inputs from geologists, seismologists, geotechnical engineers, earthquake engineers, and the structural engineer. So this was the global seismic hazard map we saw yesterday. Thereafter, we also spoken about the need for the seismic zonation, because you would like to see the varying level of ground potential shaking happening in the seismic zones. Also, you want to probabilistically map the area for the likelihood of the exceeding of the specific ground accelerations, and also you want to develop the design codes, construction practices, and also you want to enhance the structural safety in the region. Thereafter, types of zonation we also discussed about. That was the macro zonation, which is done at the national and the regional level or the continental scale, where you do consider only the inputs from seismicity or the geological features. Typically, you do not incorporate the information from the geotechnical data or site response study. You also do not take into account the secondary effect of the earthquakes. Thereafter, we did talk about microzonation. That is basically the aim of this particular course. Microzonation, we take input not only from geological or the seismological data, but also geotechnical factors, and also landslides, liquefaction, tsunami modeling, and we also perform the site response study, site characterization studies in the case of microzonation. Nanozonation considered to be a very rigorous kind of zonation, and it is considered to be impractical so far. And then we started off with microzonation, where we had the three classification: grade 1, grade 2, grade 3. Grade 1 being the general zonation, 2 being the detailed zonation, grade 3 being the rigorous zonation, and their scales of the study is also given on this slide. For the grade 1, that is similar to the national level macro zonation studies, and generally you use regional attenuation relationships for this purpose, also the available seismological record, and it is generally used to estimate the ground motions at the bedrock level. And then grade 2, it basically requires the more elaborate inputs, and you do consider the site specific attenuation relations and the recurrence relations, geotechnical data as well. Thereafter, laboratory studies such as the standard penetration test, cone penetration test, you may want to do. These are the steps of the zonation, and if you remember, we did talk about, let's suppose this is the surface you have, and then you have this bedrock, and then you have this earthquake. So earthquake's energy is coming, and then at the bedrock level you may do your analysis to find out the maps in terms of, for the first step of seismic hazard analysis. Thereafter, you will have to do the site characterization in order to characterize the soil in between the surface and the bedrock. And for site characterization, you can use invasive and non-invasive techniques, for example SPT and the CPT testing, or maybe you can go for non-invasive techniques such as the HVSR and the MAW technique. And thereafter, you have the characterization of the soil, using which you can find out the shear modulus or the shear wave velocity, which can be further used to find out the transfer function of the soils, which will help you to find out how much energy is being transferred to the surface. And then you can do liquefaction assessment, and then finally you can do the integration of the hazard. These were the microzonation and the codal provisions in India. We did talk about, and we discussed about that the 59% of the total land mass of India is considered to be prone to very large earthquakes. and we had a little bit of history about zonation studies in India, especially in 1935 after the Quetta earthquakes. GSI developed a map of seismic zonation, mainly based upon the isoseismal mapping of India and some information from the geological data. And then this map was published in 1962, had a revision in 1966, and it had over a total of 7 seismic zones based on the probable maximum intensities of the earthquakes. And these were 1962 and the 1966 seismic zonation map of India, where the Deccan Plateau, most of the part of the Deccan Plateau was considered to be the safer zone in the stable continental region. Thereafter, in 1967, the Koina earthquake happened, and in 1970, the previous map was revised. And after the revision in 1970 and 1984, the seismic zones were reduced from 7 to 5, starting from 1 to 5, based on the MMI scale. And this is the 1970 and the 1984 maps, where zone 5 was considered for most of the northeastern part of the India, some of the northern India and the western India. And in 1993, after the happening of the Latur earthquake and Jabalpur earthquake in 1997, Bhuj earthquake in 2002, and then there was a need to basically keep those zones merged with the second zonation of the 1984 map. Then the zone were reduced from 5 to 4, starting from second, based on the PGA values, and this was the final map which was published in 2002. Okay, so these were the previous studies. I want like to go through these. Now let's go ahead and start off. This was the GSHAP, which is quite important to discuss. Global Seismic Hazard Assessment Program, where Bhatia et al. In 1999, they divided the entire Indian zone for the potential seismic source zone. They considered around 86 seismic source zones, and then they prepared the PGA values, and then divided the entire Indian subcontinent into several number of seismic zones, where they considered the probabilistic seismic hazard analysis using the regional relationship or global relationship of Joyner and Boer attenuation relation. And so this was the seismic zoning map published by Bhatia. Seismic zone 1 to 4 were considered, and there were some drawbacks because they did not use the site specific attenuation relationship. The global relationships were used, that was the Joyner and Boer, and also in case of the realistic earthquakes, it was observed that the values their map was producing was actually the underestimation of the hazard. Okay. Then we had the discussion. We started off with surface waves, and with the surface waves on a seismogram are basically the longer period, larger amplitude waves that arise after the body waves. And if you look at their geometrical spreading and compare it with the body waves, then the surface waves has a smaller decay factor than the body waves, and body waves decays faster than the surface waves. And in case of surface waves, they basically cause damage to larger buildings at relatively farther distances. On the other hand, body waves caused much damage near to the epicenter, typically are higher for the buildings that are having the frequencies higher than 1 Hz. When the resonance occurs, then the smaller building will topple down. And surface waves, because they have lower frequencies which are near to the resonance frequencies of the larger buildings, and also they decay in amplitudes slower than the body waves, they affect the building further away than the buildings do. And thereafter we had two types of surface waves, Rayleigh waves, Love waves. So Rayleigh waves basically had the particle motion, that is retrograde elliptical motion, but near to the surface the particle is moving opposite to the direction of the propagation. That is why it is retrograde elliptical. So there are three axes given. You can see the here the Rayleigh wave is basically traveling here in the x direction, and in the xz plane the particle motion due to the Rayleigh wave is confined in the xz plane. So you can consider the screen as the xz plane, and the perpendicular to it is the y plane, y direction. So in the screen, along the plane of the screen, the motion of the particle is happening in retrograde elliptical motion. While for the love wave, although the love wave is also traveling in the same direction, but its particle motion is along the y coordinate. So that is perpendicular to the plane of the screen. Now this was the earthquake of magnitude 7.7, having the shallow focal depth, happened in Vanuatu Island, recorded at a station that is around 12,000 kilometers away, at a station CCM. And you can see large amplitude, low period waves, longer period waves, and these are the surface waves that you see here. These are the Rayleigh waves, and here you have love waves, and you can see the arrival time of the love waves is earlier than the Rayleigh wave. So love waves generally travels faster than the Rayleigh wave. So this is we also know that the love waves result from the SH waves that are trapped near to the surface, while the Rayleigh waves are mostly a combination of P and SV wave. So if you look at the coordinate system here, you have x, y, z. The source to the receiver joining line is known as the radial component, and xz plane the particle is moving elliptically like this, and the Rayleigh wave propagation is like this. Similar fashion, the love wave is also traveling, but the particle motion for the love wave is perpendicular to the xz plane in the y direction. So now so this is the travel time curve. On the x-axis you have the distance, on the y-axis you have the time, and because the surface waves are having very if you compare it with the body waves, then the surface waves are having the geometrical factor, attenuation factor is smaller, so they can travel around the globe multiple times. Okay, so so they can show the phenomena of multiple surface waves. So you can see, so this is the globe here, and on the globe you have this earthquake happening, and because of this earthquake the surface waves are generating, and that they are taking round of the globe multiple times. Okay, likewise similarly the waves can go also in anti-clockwise direction, and then in the fashion of the clockwise direction they may generate R1, R2 and R3 waves, and in the anti-clockwise direction they are generating R2 and R4 waves. So you can see this is the R1, then R2, this is R3 and R4, and this is what we discussed yesterday. Now we also looked at these equations for the displacement in x.
Sir, can you please go back to that coordinate system source?
This one?
Sir.
This one?
Yes.
Yes.
Sir, in this you said like so the Rayleigh and KSP. So it is I just wanted to read that it was on vertical and is radial.
Yeah, this is the radial direction joining the source to the receiver.
See, so like if anybody asks us about Rayleigh wave, which coordinating system will follow?
No, coordinate you can change according to your need. Okay, coordinates are just the reference system. Okay, but when we are looking at the particles of the Rayleigh wave, they mostly confined itself in the plane of xz, that is basically, so just consider this screen. Okay, if we consider this screen as the xz plane, and the Rayleigh wave is traveling along x direction, then the particle will be moving in the stream, in the plane of the stream, in the fashion retrograde elliptical motion. Okay, are you getting me? So this in this particular slide, yes, please go ahead.
So exact can be the plane of vibration for manic.
Yeah, exact plane will be the exact plane.
See, right, yeah.
Okay.
Vibration is exact and propagation is my
So the propagation is in the x direction.
like propagation.
Okay. So like consider this as a plane. Okay, radium is traveling like this. Okay, but the particle motion will be like this in the same plane. Okay, but this will be the particle motion of the love wave. And the love wave is also traveling in the same direction as that of the Rayleigh race. Getting me? Okay, now this in the Poisson
Solid equations for the displacement in x and the z direction, and combination of which gives the retrograde elliptical motion. And you can see displacement in the x direction and the z direction, because they have sine and cos components, so they are 90° out of phase. And in this particular figure we saw that when one is maximum, then the other component is minimum, and when other component is maximum, then the next component is minimum. Okay, so so this is what we did. Now particle motion, now we are starting the particle motion of the Rayleigh wave. If we talk about, so there is a exponential decay of the displacement, because we can write the equation, harmonic equation, in terms of the exponent, and then there is a exponential decay of the displacement, which is a function of wave number. And then in other words, you can also say that a longer wavelength Rayleigh wave will see deeper structure, which means that the larger the wavelength, you will be having the larger illumination to the deeper structure. So basically it depends upon the wavelength of the Rayleigh wave, how large is the wavelength. If the longer the wavelength, you can penetrate deeper into the earth. Okay, so mostly the Rayleigh waves are confined to the surface of the earth, but it has some penetration. And many of the studies that are conducted using the Rayleigh wave and the love wave phenomena, dispersion phenomena, people do also do model the crustal part of the earth and also the uppermost mantle part of the earth, or using the Rayleigh wave and the love wave dispersion curve. Okay, now this we have seen. Now let's move on. Yes. So dispersion we were talking about. So dispersion, we discussed about that the dispersion is basically the velocity of the surface waves is varying with frequency or with wavelength or with period. Okay, so so it is similar to the phenomena of light. In the light, what it happens, the light is falling onto the prism, and because the white light contains all the frequency content, and then as soon as it falls on the prism, then it basically divided into its several components. Okay, that is we call it the physical dispersion. But in the case of surface waves, when it goes through any heterogeneous medium, then the different component travels with different kind of velocities. So that is, we call it geometrical dispersion. So now this dispersion phenomena, because we said that the velocity of the Rayleigh wave is depending upon the wavelength, so the velocity is basically a function of wavelength. Okay, now if we talk about the representation of the velocity or the phase velocity, that is a function of two parameter, angular frequency and the wave number omega by k, where omega is basically a function of wave number. And in case of tsunami, we can also talk about tsunami. So longer periods tsunami waves do not have any dispersion if they have their wavelength comparable to the ocean floor depth. So they do not have any dispersion. But in case of shorter period tsunamis, they do also reflect the phenomena of dispersion. Okay, now if we consider, let's suppose the SH wave, love wave dispersion curves, or the love wave dispersion, because love wave is mostly consist of SH wave. So the SH wave that are traveling near to the surface like this, then some are reflected from the surface, free surface, or maybe near there might be some layer because of which the multiple reflections are happening. They may sometimes superimpose with each other because of the heterogeneity and the difference in the velocity and the anisotropy present. They may also say that show that the angular frequencies of the wave that are trapped may differ from each other slightly. So if suppose we consider there are the two harmonic waves that are being superimposed in order to generate the surface waves near to the surface of the earth, then let's suppose there is one wave which is having the angular frequency omega 1, another wave is having angular frequency omega 2, but the omega 1 is equal to omega naught plus delta omega, and omega 2 is omega naught minus delta omega. There is a slight difference in the angular frequency. Similarly, you can consider the wave number k1 and k2, k1 being the k naught plus delta k, k2 being k naught minus delta k. So if you want to find out the total displacement of these two harmonic waves, then the total displacement can be the summation of their displacement, individual displacement. So cos k1x minus omega 1t plus cos k2x minus omega 2t. Okay, so this is simple to basically carry on. So k1 is nothing but it is k naught plus delta k, k2 is k naught minus delta k. Similarly, omega 1 is omega naught plus delta omega, and omega 2 is omega naught minus delta omega. So when you will incorporate this into this particular equation here, then it will look something like this. So this should be omega naught actually, okay, and this should be k naught. Okay, all these. Okay, so now when you will rearrange all these terms, then it will basically look something like this. Okay, so when you do so and apply the formula of cos A plus cos B that we have read in our 10th standard, I suppose. So it will be cos theta plus phi plus cos theta minus phi. So you can see, so this is the same equation that you are forming here. Okay, same formula. So that will be equal to 2 cos theta, 2 cos theta into cos phi, and the displacement will become 2 cos kx minus omega t cos delta kx minus delta omega t. So what do you see here? There is one wave which is represented by this cosine function. There is another wave which is represented by this particular cosine function. And if you look at their velocity, then the velocity of this wave is basically v is equal to omega by k, and in this case the velocity will be how much? Delta omega by delta k. Okay, so this is basically the product of two cosine waves. The first has the wavelength that is 2 pi by k, and if we assume delta k is very small, because there was a very slight difference in the wave number, so delta k is very smaller than k, that the second wave will have much larger wavelength, that is lambda is equal to 2 pi by delta k. So you can imagine that there is one wave which is having larger wavelength than the other wave. Okay, so both the waves are traveling. Now if you look at it in the pictorial format, then it may look something like this. Okay, so you can see there is one envelope wave like this which is traveling, and there is some carrier wave which is having larger frequency than the envelope wave. Okay, so this wave, if you look at this wave at different times, T1, T2 and T3, then if you just consider a single point on the envelope wave like this here, in T2 it will be having displacement here, here it will be traveling here, and when you will join them together it will look something like this, right? Likewise, if you consider the carrier wave and take this point, it will reach this point in T2, and the same point will reach to this point in T3. When you join them together, it will look something like this. So what do you observe here? That the carrier wave velocity is larger than the envelope wave velocity. Okay, carrier wave velocity, if we denote it by small c, and the envelope wave velocity, if we denote it by small u or the capital U, then u is less than c. Do you agree? Did you get me? Okay. Or should I explain it again? Okay, so u is less than c here. So what you can see, there is envelope wave which is traveling with a smaller velocity than the carrier wave, right? Now, hence the first cosine term defines a wave which is sometimes also called as carrier wave, that is modulated by a slower varying envelope. Okay. Since the velocity with which a wave defined is u is equal to cos ax minus omega t, which propagates with a velocity of b by a. So this is ax minus bt, I think. Okay, so b upon a is the velocity of this wave. The velocity of the carrier wave is v is equal to omega by k, and that the envelope is slower, the velocity is delta omega by delta k. So this is what we just saw here, right? So here if you will see, we saw that there is this, this is the carrier wave, this is the envelope wave. So carrier wave velocity is omega by k, envelope wave velocity is delta omega by delta k. And envelope wave velocity is smaller than the carrier wave velocity, we just saw that. So we refer to the former as the phase velocity and the latter as the group velocity. So you can call the envelope wave velocity as the group velocity and the carrier wave velocity as the phase velocity. Okay. So, so basically phase velocity will be represented by small c and the group velocity will be represented by u, and there u is less than c, right? So typically c is used to denote the phase velocity and u to denote the group velocity. The relationship c also can be written as the velocity of the phase, that because we are calling it as a phase velocity, and that is equal to omega by k. And the group velocity is capital U, or we can call it the group velocity V group, and that is equal to del omega by del k. If suppose del omega and del k, as we are considering, is almost tending towards 0, very small, so it can also be written as d omega by dk, right? Now we also know that the phase velocity is omega by k, omega as a function of wave number. So if we want to develop the relationship between c and u, phase velocity and the group velocity with respect to the angular frequency, then we can basically use this particular formula, u is equal to dw by dk. And you know that omega is what? It is equal to ck from this. So omega is ck. So when you incorporate that into this formula ck and use the chain rule to differentiate with respect to k, then it will become k dc by dk plus c dk by dk. So that will be equal to 1. So you will be getting k dc by dk plus c. That is the expression you have. So u is basically k dc by dk plus c, that you have it here. And if you want to develop the relationship in the terms of lambda and the group velocity, then you can do the operation further. For example, if you suppose have dc by dk, you can basically multiply the denominator and the numerator by d lambda, then it will be dc into d lambda divided by d lambda into dk. Okay, and you know that k is equal to what? 2 pi by lambda, right? So you can calculate dk by d lambda and then incorporate it into this particular equation. Okay, so when you do so, this will become dc by d lambda in bracket minus 2 pi by k square. and then we can convert this to wavelength. So from the previous equation where we saw that the k dc by dk plus c is equal to u, so we can again multiply this term numerator and the denominator by d lambda, and we saw that this particular thing is nothing but this, and we incorporate this here. So k dc by d lambda in bracket 2 pi by k square plus c, and it will finally become like this. Okay, c minus 2 pi lambda dc by d lambda, and in practice you generally drop the 2 pi term in order to have the broader view of the relationship. So u is equal to c minus lambda dc by d lambda, that is the relation we generally get. So at greater depth in the earth tend to have higher velocities. So you know, as you go deeper the velocities will become higher. So so c basically increases with lambda. Okay, so as I told you, like as you go deeper the velocity is higher and higher wavelength penetrate deeper. So dc by d lambda will be always greater than 0. So from the above relationship, if this is greater than 0, then u should be less than c, right? So here it is, this is what it is written. Now if you talk about non-dispersive medium, so in the non-dispersive medium what will happen? There will be no change in the velocity with respect to the wavelength. That means dc by d lambda will become 0, and then you will finally get u is equal to c. That means the carrier wave velocity is equal to envelope velocity, or the phase velocity is equal to the group velocity. Okay, so this is the dispersion curve with respect to period on the x-axis, and here you have the group velocities and the phase velocities for a synthetic model which has two layers, where the velocities of shear waves for the first layer is 3.9 kilometer per second. For the second medium the velocities are 4.6 kilometer per second. Likewise the density is given for the first layer and the second layer, and the thickness of the first layer is given. So second layer is basically a half space. Okay, so when you construct the synthetic love wave dispersion curve for group and the phase velocities, then it will look something like this. So in this particular thing, what you see, this in this dispersion curve, c is above u and c is always greater than u, or you can say u is less than c. Okay, so if we go further and would like to see the dispersion phenomena in the real earth scenario, so you see here there is this love waves recorded for a Californian earthquake recorded in New York, and you see in these love waves there are the peaks and the troughs. This is the trough, these are the peaks, all these are marked. Okay, and if suppose we want to calculate the group velocities for these love waves, because group velocities are mostly very easy to measure, because you do not need any information of source or something. And in this case for this particular curve, because it is a filtered curve, so you filtered seismogram, so you can easily compute the group velocities. So how to compute that group velocities? Because if you look at it very carefully, then peak to peak distance, if you look at it, this is the peak to peak distance, here it is the peak to peak distance, peak to peak distance, it is gradually with time decreasing. So this is what we should have observed, as we discussed yesterday also. So with respect to time, the peak to peak distance is decreasing, which means that the velocities of these different frequencies are varying with time. And here you observe the higher period at the very beginning, so these are higher period, and gradually the periods are decreasing. So higher periods are traveling faster than the slower period. Okay, this is the phenomena of dispersion. So in order to find out the group velocities, let's suppose you want to find out the group velocities for this particular period, then you can calculate the distance from where this earthquake is coming from, okay, and also the arrival time from the x-axis, and then distance divided by, so the velocity will be what? Velocity will be distance that you already know maybe let's suppose the distance is let's suppose 4300 kilometer divided by the time of this particular peak is 1140, so maybe 3 point maybe 7 or something kilometer per second you will observe. Okay, so that is the group velocity. Likewise, for the consecutive peaks in the similar fashion, if we call it V1, then V2 you can calculate 4300 divided by, for this peak it may be maybe 1150 or something, and you will observe 3.6 kilometer per second. So gradually for the successive peaks you can measure the group velocities. Okay, and for the successive peaks you can also measure the periods. So for example, let's suppose the period of this maybe 10 seconds, here you have the period maybe let's suppose 20 seconds, 30 seconds, likewise you have. Okay, in order to construct your dispersion curve with respect to the period, here you can have the group velocities, here you can have the period. Okay, and then this is 10, this is 20 maybe, this is 30 maybe, likewise you have on the x-axis, and the group velocities you have already calculated. Okay, so when you will mark those points with respect in this particular graph with respect to group velocity and the period, and then join them together, and this will be your final dispersion curve. Okay, and then so this is what this calculation is being shown here in this particular slide. Now if we move on, now look at this particular example. This is the Mongolian earthquake recorded in Japan, and you can see that the first seismogram is unfiltered. Okay, and then you have filtered the seismogram for a period of 14.5 seconds. Thereafter you have filtered the seismogram for a period of 19 seconds. Thereafter you have filtered the seismogram for a period of 28 seconds, and then 51 and the 109 seconds. Okay, on the x-axis the group velocities are also calculated, but what you see, the lower periods are coming somewhere here. Thereafter you can see higher periods are gradually arriving earlier on the seismogram. Okay, so this is what it is. It can be concluded from this: the higher periods are traveling faster, and the smaller period are traveling slower. Okay, so when we construct our dispersion curve also, it was the phenomena that we saw, like the higher periods are traveling faster, higher periods are having higher group velocities. Okay, now so how these dispersion curves are useful? Okay, this is the main study. So now look at this example. This is the ridge here in the mid-Atlantic region, and there is some earthquake happened at this particular point, and there is this particular station which has recorded the earthquake. Okay, so the rays will pass through exactly over the ridge region, and there is another station with the station code WIN, WIN WIN, and the rays will pass through like this. Okay, that is off the ridge, and there is one path which is on the ridge. Okay, so when you use your seismogram recording at both the stations and then filter them out and then construct your group velocity dispersion curves, then your dispersion curve may look something like this. Okay, so this is the on ridge dispersion curve, and this is the off ridge dispersion curve. Okay, off ridge dispersion curves are having higher velocities in comparison to the on ridge dispersion curve. That means off ridge or the on ridge dispersion curve, because it has slower group velocities, that is made up of some slower material, low velocity material. Okay, maybe some kind of hot spot is present there or something. Okay, and if you will model it using some kind of inverse technique, then your model may look something like this. The black thick line is representing the off ridge model, and the thin black line is representing the on ridge model. Okay, so you can easily see that the off ridge model is depicting the higher velocities in comparison to the on-ridge model. Okay, that is also indicating towards there might be a possibility of slower velocity model underneath the ridge. That may be true because underneath the ridge there might be some magma present or maybe some kind of hot spot present. Okay, so surface waves are a function, surface waves, group velocities and the phase velocities are a function of P wave, shear wave and the density. So this is what we saw. So group velocity, we converted it into the shear wave velocity model, or P wave velocity model we can convert it, or the density model we can convert it. So this is what it is written: surface wave phase and the group velocities are a function of P wave velocity and the S wave velocity. Okay, in practice they are most sensitive to.
So, for really is you begin the distortion curves. There will be the system and vertical with the begin, but just on index. Generally, we take for the group velocities for the relay, we generally take the vertical component. Okay.
Okay, now, yeah, so like if suppose somebody is interested to model these dispersion curves, there is a great great repository of the codes are available online. One I would like to mention by Robert Bob Herman from St. Louis University. There is this code available which can be used to model your dispersion curves. Now look at this example. Okay, in this example, this is a very famous example by Nishimura and Forsyth in 1989, which is the one of the most commonly shown figures in seismology and the relative fields for 5 age provinces in the Pacific Ocean or the Pacific Basin. So you can see these dispersion curves are computed for different age crust for in the Pacific Basin. So you can see one is for 0 to 4 million years, another is for 4 to 20 million years, and then 20 to 52, 52 to 110 million years, 110 plus million years. Okay, so this is the oldest and this is the youngest. Okay, so all these dispersion curves are computed for Rayleigh wave phase velocities as a function of the oceanic plate age, and when you will model them, then you will get your shear wave velocities with respect to depth, something like this, where you can see that the younger material is showing lower shear wave velocities and then the oldest material is showing the highest velocities. Okay. Now let's have a little bit talk about the tsunamis. Okay. Okay, tsunamis. Okay, dispersion is also observed in tsunamis. The water waves generated by the earthquakes. So when there is a earthquake in the fault situated into the ocean, there will be the displacement of the water column because of the earthquake or the fault movement, and then the water column will move with the kinetic energy towards the shore. As it reaches to the shore, the energy converts to the potential energy, which will give rise to the height of the waves, and that we generally call it tsunami. Okay, so tsunami dispersion is also similar to the Rayleigh and the Love wave. Or in tsunami dispersions, also the longer waves, longer period waves travel faster and thus arrive earlier. So if you look at the tsunami, the dispersion basically depends upon its wavelength. So the wavelength is that large, if it is comparable to the water column depth, then you won't see any dispersion in there. So for the dispersion phenomena in the tsunami, you should have your wavelength smaller than the water column depth, water flow depth, then only you will see dispersion. So in case of non-dispersive tsunami, the phase velocities will be equal to under root GD. So this is the most common formula you might have seen for the tsunami. So but that is for the non-dispersive tsunami. for the shallow ocean floor depth. Okay, and for the longer wavelength and the deeper depth. And in case the shorter wavelength, the phase will basically depending upon lambda. That means it will be a function of wavelength, and the formula will be C is equal to under root lambda G upon 2 pi. Okay, so hence water wave group and the phase velocities here do not match and basically show the dispersion phenomena. So if you look at the group velocities and the phase velocities of the tsunami waves, then just look at this figure here. So what do you observe in this figure? So here you have the larger value of the period, and if you go from left to right, the value of the period is reducing. Okay, and if you concentrate yourself into this portion of this graph, then what you observe, for the higher period, the value of C and U are almost equal. Okay, they are all flat for each. Either you would look at 6 kilometer wavelength or 4 kilometer or 2 kilometer. Okay, all these are equal. That means in the case of higher periods, the dispersion phenomena is almost negligible in case of tsunami. Okay, but if you look at the smaller period, then you see there is a difference in the group and the phase velocities. That means the dispersion phenomena is happening in case of the tsunami but for shorter period. Okay, so this is the real data example here that you are seeing. So what we have discussed theoretically just a while ago is actually happening in the case of real tsunami scenarios. Okay, now this is the tsunami recording here that you see. What do you observe here? The same thing that we just saw in the case of earthquakes as well. Okay, for the surface wave. So in the case of tsunami also you see the peaks are the period are larger here, then it becomes smaller, even smaller, much smaller, like this it is keep going. That means the tsunami phenomena for the shorter periods also is displaying the dispersion. Okay, so now if you look at okay, so what is the takeaway here? So like dispersion phenomena is a very important phenomena which basically give the value of phase velocity or the group velocity for the Love wave and the Rayleigh wave with respect to either wavelength, with respect to either frequency, or with respect to either period. Okay, this is what you are going to construct the dispersion curve in the case of the engineering seismology, where you are going to do the seismic site characterization of the soil. Okay, so as I told you in the just a while ago, like there is this surface, there is this bedrock, and in between you have soil. And when you do the site characterization using non-invasive techniques such as SASW spectral analysis of surface wave or the multi-channel analysis of surface wave, then you will have to construct the dispersion curves. Okay, so using the dispersion curves, once you construct it, you need to model it. You will have to model it either using some kind of forward modeling technique or maybe some kind of inversion you can do. There are several softwares available that you may use it for the modeling purposes. Okay, so so while you do so, you will get your model in terms of shear wave velocity, and here you will be having shear wave velocity, here you will be having depth, and this is what you need to basically construct using your dispersion curve. And this shear wave velocity model will further give you the information about the elastic parameters of the soil that you can use it for site response analysis. So in site response analysis, the amplification factor or the transfer functions you might be computing, and I think you might have studied about linear site response analysis, equivalent linear site response analysis, or maybe the non-linear site response analysis. So where you will be basically following the stress strain curve in order to find out the transfer function for the soil. Okay, so once you convert, once you have the transfer function, you can easily compute how much energy that is available at the bedrock in terms of the ground motion is transferring to the surface. So our aim is to find out how much ground motion is there that is occurring at the surface of the earth where you are going to construct your buildings, right? So for the safer construction designs, you will have to go through those micro-zonation steps one by one. So like first you need to make your maps for the PGA or the spectral acceleration at the bedrock level, and thereafter you may do the site characterization, and then you come to the surface using the site response study to find out your PGA values at the surface. And if further analysis is required for the landslide and liquefaction, then also you may do so. So now if I will ask you that the dispersion curves that you have just seen, like you can construct these dispersion curves in the field also, you might have studied about the array of the geophones in the MASW techniques, where you keep a geode and that is connected to several geophones in a channel, and then you place it in an array into the field. Thereafter you basically using the active source or the passive source, you are generating some kind of source energy, and that is being recorded at several geophones in the array. And then you do some kind of processing, and thereafter you are coming up with the dispersion. Okay, so the dispersion is an important phenomena, and we may want to use it for the modeling of our subsurface of the earth. Okay, so this is what we wanted to discuss about. I think that is all for today. We will discuss further tomorrow. Thank you so much. Any question?
Sir, with respect to earthquake magnitude, whether register changes with respect to its magnitude. No, that is not a function of the magnitude, because that is the elastic parameter of the soil. Okay. So with respect to magnitude, the velocity of the shear wave in a material doesn't change.
What is the maximum that with the surface waves can penetrate?
In case of an earthquake, I have seen the studies being constructed up to the uppermost mantle. Okay, 200 kilometer, 300 kilometers. Any other question?
So during one of your slide, you said that sickle wave is all at half space. I don't see it there.
No, half space means at one end it is fixed, and another end it is going up to the infinite depth. That is what we call it as a half space. So, for example, this is the surface of the earth. Okay, and there you have one layer. So this is your layer one. Okay, and thereafter we are considering half space. Half space means you do not have any depth. It is going infinitely deeper, but at one end it is fixed. So, any other question?
Excellent. This question is for Gupta sir. Are you sure the slide in which there are a number of ones we think is of RTR, 1999, where it is 86.
No, those were source.
Source ones.
Yes.
So depending on source zones, whether PJ value changes for each source zone, suppose we reduce that source zone from 86 to 20. So for each node, the PJ will change.
Yeah, the PGA will change because you are considering the lesser number of zones. So in PSHA, what you generally do, you try to find out the distance between the site of interest and the source, right? So number of sources you have reduced, automatically the distances will also change. And when you incorporate those distances into the attenuation relationships, okay, then the PGA values will also change, because attenuation relationship finally give you the PGA values.
So for obtaining better PG values,
You need to have a good idea about the geology of the area where the what is the exact location of the sources of the faults. There might be some buried fault also that you may also look at.
But John, wait till you join the company. He was big. I told me things. He used some to certain. So, okay.